Okay, thank you. In this third lecture, I will, the first part will be to prove the theorem that I stated yesterday, and I will restate it now. So, you consider a random walk on the free group on R generators, given by a probability measure. There exists a current T, a bifurcation current of dimension P-1, P-1, where P is the dimension of the variety of representation of the free group in PSL to C. That we denoted by lambda of FR.
Just 3R.
Right. No. Yeah. I don't take the quotient by the conjugation. So that for any complex number T, and for almost every random sequence chosen so I recall that we choose some elements in FR randomly with a distribution nu and independently. And we consider the product of the first n elements of this sequence, and at each time we multiply on the right. So we consider the right random walk, and then we consider the following variety. This is the set of representations. So this is the R tuple of matrices. Such that if you look at the image of the word of the random composition at time n, the trace of the matrix you have is T. So we take the square because the trace is not defined on PSL to C. So I recall that so you take the square, so I will denote it really like if it was a representation this time. So you take the image by this representation of the random word that you have of length n, and you want that this is equal, the trace is equal to T. Okay, so this is a codimension one submanifold. And if you divide, so you consider this divisor, you divide by 2n, and in the sense of current, it converges towards the bifurcation current. Okay. So this is the equidistribution statement. But as I said yesterday, this is quite easy. The difficult part, I mean, really the theorem is that, moreover, this bifurcation current has support the bifurcation locus. Okay. So I will explain a little bit the ideas to prove the equidistribution result, and then I will focus on the proof of the support theorem, namely that the support of TBIF is exactly the bifurcation locus. But first, I will indicate how we prove the equidistribution result.
So the equidistribution is just the competence of this sequence?
Yes.
But this is not just the degree, control the degree? That's it.
If you control the degree, there is a subsequence which converges to something. Okay? But first, here, there is no subsequence. You just... And it always converges to the same thing. Okay? It does not depend on the sequence. It does not depend on T. Yes? Yes, he said that this is an algebraic manifold of degree at most n. Affine. It is given by polynomial equations. If you take the product of n matrices and you take the trace, it is a polynomial in the coefficients of the matrices of degree at most linear in n. And in fact, exactly n. So you have a affine manifold defined by an equation of degree n. If you divide by n, in the sense of currents, you can extract some subsequences. So, of course, yes, we are in an affine manifold also, so maybe this current could go to infinity also. So, okay, yeah, you're right. We don't...
Get an idea of the degree of
Yes, this algebraic variety has degree n. I mean, it has degree bounded by n. I don't know if really it has degree n because there is maybe some simplifications. So the idea to prove the statement about currents is, so I recall, or so what does it mean? That, so a current, what it is an operator which assigns to p-1, p-1 form a number. And so this, as a current, is just integrating a form, p-1 form, p-1 form, on this submanifold, because I mentioned one submanifold. And then we divide by 2n, and the statement says that it converges. So how we prove this kind of convergence? We use potential theory. Namely, we are going to write these currents as the Laplacian of some function. These currents are positive currents, so these functions will be purely subharmonic functions. And then to prove that this convergence is, it is sufficient to prove that the potentials converges in L1, locally in L1. So what is the potential of a submanifold defined by an equation? So the equation of this submanifold is there. It is, so this is the Poincaré-Lelong equation. You have that this current, so let's do it. This is the Laplacian. So for those that don't use currents often, you can think that we are. I mean, you can just think that we have a curve in the holomorphic curve in the set of representation of the group FR. Okay. Then this set is going to be a finite subset, codimension once a manifold, and this convergence just says that this finite set, if you consider the equidistribution measure on that set, converges to some measure. So you can really think that the objects that we are considering are measures, if you are not. Okay, so what is the Poincaré-Lelong equation? It says that a divisor as a current is the Laplacian of the following potential, which is the logarithm of the norm of the equation. Okay. So, as I said, to prove this convergence, we have to prove that this, we can prove that this sequence of potentials converges in L1 log. So we have to understand the limit of these functions as n tends to infinity. Okay, so we have what we have here. So let's just don't think about L1, just do it at each parameter, just to see, to guess what is the limit. So we take a random product of n matrices here. We have seen in the talk by Christian that this is a matrix which is going to be really large because the representation, for a generic representation, it will be non-elementary, so it's going to grow exponentially. But we don't look at the norm, we look at the trace. Okay. So I recall that there is this result by Furstenberg, which says that if A is non-elementary, then there exists a number which is called the Lyapunov exponent of the representation and of the measure mu, such that for almost every random walk, we have the following, that if you look at the image of the n step of the random walk by the representation, this is going to be a matrix whose norm is exponential, and the rate of this sequence is exactly that number, which is the Lyapunov exponent. And so the fact that this limit exists is more or less a consequence of the subadditive ergodic theorem. But what is important here is that the Lyapunov exponent is strictly positive. It's a positive number. So you have really an exponential expansion for the random products. Okay?
Where is A in the left?
Sorry? So where is A?
A of our image.
Sorry, yes, okay. Right. You take the image by the representation. You take the n-step random walk, and you take the image by the representation. Okay? So now I will just indicate, so the precise thing that we want at a fixed parameter is a theorem by Givash, which uses a lot of materials, but it is exactly what we want. Namely, under the same hypothesis, if A is non-elementary, then implied that for mu almost every sequence, we don't look at the norm, we look at the trace. We take the log, of the trace of A of Rn of G, and this is going to tend to the Lyapunov exponent, which is defined just here. And I will explain the idea of that theorem. So the proof uses a lot of difficult material about random matrix products, but we can try to understand why, for a random matrix, the norm is approximately the same thing as the trace. Okay, so I will explain that now. And this will serve for the rest of the... But just before, I just say the following. So here we can guess from Guivarch's theorem what will be the bifurcation current. It will be the DDC of the Lyapunov exponent function. And by a theorem by Lepage, we know that this function is continuous and even more older on the open set of non-elementary representation. So it's a good function, and so the bifurcation current will be a Hölder, will have Hölder regularity. So it's a nice current also. So let me just explain some basic facts about matrices with really large norms. So let me explain something which is basically the polar decomposition of a matrix, but I prefer to explain to see that geometrically. So so take M a matrix with large norm. Okay, then you can prove, it's easy, that there exist two balls in the sphere, one that I will call attractive.
You put the permission, usual permission metric.
Right, put the spherical metric on the sphere, okay? And we will look at the action of this matrix on the sphere as a Möbius map. So I claim that there exist two balls, an attractive one and a repelling one, balls of diameter of the order of magnitude of the inverse of the norm.
Balls where?
Balls contained in the Riemann sphere. Okay, whose diameter of the order of magnitude of the inverse of the norm of the matrix, and which are such that M is going to map the exterior of the repelling ball onto the attracting ball. Okay, so you have the sphere, and you have two balls, which are really small because the norm is large, and the exterior of the repelling one, so is mapped, so there is on the attractive one. Okay? So of course, and these balls, they are not well defined. I mean, you can move a little bit, but they are well defined at an error of 1 over the norm. Also, so okay, and what happens is that it is easy to verify that if the attracting ball is not too close to the repelling ball, then the trace is approximately the same as the norm at up to a bounded constant. Okay, so if you prove that for most of the random product, the attracting ball is far from the repelling ball, then you prove that the trace is the same as the norm, approximately, and these limits will be equal. So this is the idea in Guivarch's theorem, but then you need really precise estimates. Okay?
So that is also not always true.
What is not always true?
That M is PSL2C with last norm as that. If M square is, if you take the...
This is always true. This is always true. This is the K-AK decomposition. Okay, proof. You can always write a matrix as a matrix in SU2 times the diagonal matrix times another matrix in SU2. Okay? Then a diagonal matrix, it's clear that it is. So the norm of the matrix A is the same as the norm of the matrix M. So A is big. So for A is clear because you have point at infinitive. And then the balls attracting and repelling are the image of the ball around 0 and the ball around infinity by K1 and K2. Think about that. This is this is really, so this is a geometric interpretation of...
If K1 sends the ball around 0 and the ball around the other and reciprocally. That is, you have your attracting, repelling, and you make half of a quarter of term.
So you are speaking about parabolic matrix.
Oh, yeah.
And the four
no? I mean, you have to rotate, and you make the wrong rotation, then that's what we say, perhaps they cancel out.
No, they don't cancel. What happens is that, in the case you consider, the attracting ball is the same as the repelling ball. That's just what happens. And in fact, you are close to be a parabolic map.
But you have just matrix, so that M square is not.
Yes, but still.
But they have.
Still, this is true. I mean, still.
If M square is the identity, you don't have attracting anything.
No. The thing is that this decomposition is not stable by product. It's really so. It's really hard to. So if you take two. Yeah, it's not really. I mean. But what I mean by attracting is the fact that almost all the sphere is sent to the attracting point, and the repelling point is that. Okay, this is the meaning of that. So.
This gives a picture of M, but not of M square.
Right. M square is a product of two metrics of large norm, and the K-AK decomposition is really bad. Okay? But if you take a matrix of large norm and you multiply it by a matrix of norm, say 10, then we will see, then it is really possible to understand what happens for the decomposition. So let me write that. It's really easy, but it will serve. Okay, so let me take my notes. So take M. So M is a matrix of large norm, and then because we are considering a left random walk, we are going. So suppose M is the n step of your random walk. Then the n plus 1 term you multiply on the right by another matrix, which I denote by A. So it is going to be, if the random walk is given by multiplying by the generators and their inverses, is going to be something like this. Okay? So I claim that the attracting ball of this one is the same as the attracting ball of M. So it's not exactly the same. I say that they are defined up to some, but because the errors are exponential, up to an exponential error, this is true. And the repelling ball is approximately, so this repelling ball is going to move a lot. That one does not move, but that one moves by Okay, because here almost all the sphere is mapped by M to a small ball. But so almost all the sphere will, I mean, I let you think about that. I prefer because So what does it mean? It means that if you take a large random composition, so you consider, so now really I take M is equal to R, A of Rn, Rn of G. M is going to move almost all the sphere to some points, to some really small ball around the point which is going, so this is the attractive ball. And there is a point which is going such that if you take out a neighborhood, a small neighborhood of that point, almost everything is going to map there. But this point is going to follow some random walk given by the inverse process. Because here, as you see, there is a change of sign. So that means that the attracting balls converges to some points on the sphere that I will denote by theta A of G. So this is a really important map, as we will see. So this is a map which is defined almost everywhere on Gn with values in P1. And the repelling point, which is not going to be really important for us, but just to explain the Givard theorem, follow a random walk on the sphere. And so it's, I mean, you can imagine that this random walk is going to be far from that ball for a lot of time. Okay, so that explains why the repelling and attracting ball of that random walk are going to be separated for most of the times, and why, I mean, the heuristics which explains Givard's theorem. But Givard's theorem is far from being easy. You need exponential estimate for the convolutional operator associated to the inverse random walk.
And this argument was for every word or for almost every word?
So it works for almost every word. In fact, it works, yeah. It works for every sequence of words such that you know that the norm tends to infinity. The norm of the products tends to infinity exponentially. No, this is basically this is Osseledet's arguments. Okay, so it works in any dimension.
So in that case, you have put probability to the words, to the generators AI1 over the number. I mean, you put the probability in AI, which is equidistributed.
Right, you do that.
And then you consider the
right. For instance, yeah.
Probability to the product probability, and then with respect to almost every word in respect to that probability.
Right.
This statement is correct.
Right. Right.
Well, if you want in higher dimension, we need that the spectrum, the larger version of the exponent is simple.
Right. Yes. But you have these kind of theorems, yes. So that's okay. Okay. So I want to I will not speak more about equidistribution statements. Then, so we have the limit that we want at a given point, and then we have to prove that in fact this limit holds also in L1 log. And it uses continuity of the Lyapunov exponent functions and a version of Hartog's lemma. But I don't want to say it's not difficult. In fact, it's not really difficult. So let me just say, before going more into the proof of the support theorem, let just me say some words about from where this work come from. In fact, they were before we begin to work on that question. Romain was interested in the same kind of bifurcation currents on but for other kind of dynamical systems, which are the rational maps acting on the sphere. And in fact, the theory of the bifurcation for these dynamical systems was studied before in this vine. Namely, Laura DeMarco defined a bifurcation current for holomorphic families of rational maps. And these bifurcation currents, what it is, for those who knows a bit about the dynamics of rational maps on P1, it is also, in this context, the DDC, so the Laplacian, of the Lyapunov exponent of the measure of maximal entropy for that rational map. This is also the DDC of the Lyapunov exponent for a canonical measure, important measure. And then there were some works by Romain Dujardin and Charles Favre, and also by Bassanelli and Berthelot, who proved after that. So Marco defined this current, and also she proved that she proved the support theorem. She proved that the support of that bifurcation current is exactly the set of points where the dynamics bifurcate. And then came equidistribution theorem after that. And in fact, the logic is a little bit in the opposite sense here, because first we prove it's not really difficult to prove that the support is of the bifurcation current is a bifurcation locus, and then after that came the equidistribution theorem. Okay, but the proofs. So here, for instance, the proof of that support theorem here uses really much the dynamics of the critical points of the rational maps. And the analogy, I mean, was not clear at all. What should we take for the Kleinian groups? And we had to go in different directions.
Could you recall this operator DDC is related to Laplacian?
Yes.
Is it Laplacian or?
It is a Laplacian. So if the complex manifold you consider is a Riemann surface, it is the Laplacian.
So in particular, this statement says that if you're in a region of structural stability, I guess, then this function is harmonic.
Right.
The Lyapunov exponent is a harmonic function on the part where the
right.
dynamics is
exactly
stable. And then when you arrive at the boundary, if you take the Laplacian, you get this kind of object.
Right.
This current supported exactly
on the boundary. Yeah. Right. So, for instance, the good example to have in mind here, which was so much before all these works, but this family of quadratic maps. So here, if you are in the C-plane, you have the Mandelbrot set, like this, etc. And here, for instance, if you look at the Lyapunov exponent on this plane, this is interesting to see what happens if you are inside the Mandelbrot set. Then the Lyapunov exponent is log 2. And then outside, it's going to be, so it's hard to understand exactly what happens on the boundary. But then outside,
log 2 on every component?
On every component there. Okay, so this is the components, connectedness of the Julia set. And then outside, the Lyapunov exponent, so you have stability, but the Julia set here is a counter set. And the Lyapunov exponent is a function which is going to be bigger than log 2 and going to infinity.
So why is
it is log 2, it is related to the fact that the dimension of the measure of max. Sorry?
Because it's different too.
It is related to the fact that the dimension of the measure of maximal entropy is 1. This is a Makarov theorem, and I don't know exactly in that setting who proved, maybe Nessim, you know that well, who proved that the dimension. Urbansky, Pritsky, maybe? I don't know exactly well.
Bifurcation current appeared first because you consider the green function in both variables. And
Right.
when you restrict to the critical set, you get the harmonic measure of this of the Mandelbrot set.
I see, okay.
And that's the way it appears.
Okay.
Is it rolling measure? One? No.
So, Brownian measure, what it is?
No, because rolling measure is in the slices. When you see, you get the measure.
No, in the
This
dynamic
is
case,
if you consider.
But then actually, I mean, if it's a green function, as you say, then the only information contained here is that it's embedded in the complex plane. I mean, there's no further, from the set already you obtain what the current is, in this case. Because it's just, you take the green function of the complement, of the two parts, is that correct or not? Canonically you associate the two.
Maybe at the end.
Okay. So, so I wanted just to say that there is a counterpart which existed on the side of rational maps acting on P1, but I don't think the time will permit to do that. So we can really make an analogy of that picture in the context of Kleinian groups and bifurcation currents of holomorphic families of groups, but I will not have time, I think. Anyway, so I come back to the proof of the support theorem in this context of representation of groups. So, as I said before, if you take at one parameter, you take the image of the random walk on the free group in SL2C, you see matrices who are going to attract on a point almost every part of the sphere to a point of the sphere which will converge to some point theta of G as infinity. And this function is called a boundary map. So I will explain some so it is called a boundary map because in fact it induces a map which is measurable from the Poisson boundary of G to P1. And I will not define the Poisson boundary here, but I will give you an example. So here we have to deal with the free group on R generator, on which we have a measure. So G here is a free group on R generators. So if you take the free group, so let's do the picture for R is equal to 2. Let's draw the Cayley graph of that group, and we can look at the random walk of the group as a random walk on this graph. This graph is hyperbolic, and it has a boundary, which is the boundary of the group, the free group, which is a counter set. And it can be proved that if you take a point and you start the random walk on the graph, then this random walk is going to tend to some point in the boundary in this boundary. And in fact, the map, so here you have random sequences of points, and to a random sequence of points you associate a point in P1, but this random sequence of points converges to a point on the boundary of the free group, and the map, and you can define, you can well define the map, a priori it's not clear, but you can well define the map which associates to this point in the boundary of the free group, a point in P1. And at the end of that, what you get is that the map theta A, it's better to think of this as being a map from the boundary of the free group equipped with some measure called a stationary measure to the Riemann sphere equipped also with, so let's call this stationary measure nu0 to another stationary measure on P1. And this map is equivariant with respect, so of course the free group acts on its boundary, okay? And here you have the action given by your representation. Okay? So so here I don't want to explain what is the Poisson boundary, but for those who know a little bit, I just recall that in fact the Poisson boundary has to do with the tail algebra, the tail subsigma algebra of G to the n, namely you identify sequences if they are, I mean, if the right random walks are equal for n big enough. Okay? So this is just that. This is the definition. This is the tail algebra of G to the n. And of course, you see that the limit of these attracting balls does not depend. I mean, if these guys are equal for n big enough, these attracting balls are going to be the same, and so theta defines a map from the boundary, from the Poisson boundary to the Riemann sphere. And so now the support theorem will have to do with the following concept, which is really close to the concept of holomorphic motion, but which is a kind of measurable version of what is a holomorphic motion. And it has the big difference, a priori, that for holomorphic motion, you take a set of the Riemann sphere and you move it holomorphically, but you want that the points there is no collision between the points. But here for in this measurable notion, a priori the points can have collisions. So let me state, so we will call that a holomorphic variation of the Poisson boundary. I don't know if it is a good terminology, but on an open set U inside the set of representations that we are considering. Okay, is a map theta from E times U in P1, where E is a measurable subset of the Poisson boundary. So E is a subset of the Poisson boundary of full measure. Sorry, it's a... And you ask that this map is holomorphic with respect to the variable in U, and is equivariant, namely, for any element with respect to the variables in E, namely for any element, if you fix an element in U, then the map theta is a boundary map in the sense that we just defined before. So it is a J equivalent, A equivalent map. Okay? So it is equivariant with respect to the E variable. And it is holomorphic with respect to the variable, to the U variable.
This Poisson boundary is a circle?
Is a circle?
It's a circle.
No, here is a Poisson boundary. Here is it's a measure on the geometric boundary.
There's no geometric representation like a circle or something like that.
So if, for instance, you start with the group of a surface, for instance.
No, with the free group as well. I mean, you're taking here free group, no?
Yes. So here, if you have the free group, then the Poisson boundary is identifies with a measure on the geometric boundary of the free group, which is a counter set.
It's not a circle.
It's not circle, it's a counter set.
Can you say together the support of mu is on the limit set of something? No?
Right, exactly. So here, nu is supported on the limit set, has support exactly the limit set of the representation at A, of the representation A. Okay. Okay. So now let me just state the two steps of the proof. So what we have to prove. We have to prove the following statement. That is, if you take U, a subset of lambda representation of the free group, an open set, in which the bifurcation current vanish, then we have to prove that on this set, the representation are structurally stable or algebraic stable, as we saw in the first lectures. We have to prove this statement, which is the hard part. The other part is really easy. Implies that U is in the stability locus. And the proof goes as follows. I mean, the sketch, the strategy is the following. So first, we prove that, so first step, we prove that under this hypothesis, if the bifurcation current vanishes on U, then in fact there exists a holomorphic variation of the Poisson boundary on any compact subset of U. And second step, we prove that an holomorphic variation of this Poisson boundary is indeed a holomorphic motion. And then
for holomorphic motion, you need to embed the thing in some plane, no? Here you have this Poisson boundary is where?
Okay, so let me just.
You have to embed it in the plane.
Right. So so you can think for any element of E, you can take the graph of theta on U times P1. So let's do that. I think it will be clear. So for any E, we consider the map theta of E on the set U, which is holomorphic, and we can look at its graph. And we obtain, if you take all the points of E, we obtain a lot of graph, which depends measurably on E. To say that it is a holomorphic motion is saying that, in fact, these graphs are disjoint. They do not intersect. Okay? So a priori, it is not clear that holds. Okay? You could imagine that there is some variation, measurable variation, where the graphs intersect, but the theorem says that this is never the case. And in fact, it's not. Okay, so a holomorphic variation of is a holomorphic motion. And so, as we sketched the first lecture, this implies stability. So, let me finish by explaining the idea of the proof of these two parts, of these two steps. In fact, the idea is to consider to take this product, U times P1, and on this product, we have a dynamical system, which is, in a sense, quite trivial. I mean, it's trivial in one direction and non-trivial in the other. You make the free group acting on that. On each fiber, it acts by the corresponding representation. Okay, so you consider the action of all your representation line by line. Okay? And what we are going to do is the following. We start with a horizontal. So we are going to look at the action of the group on the set of sections. Okay? And we will look at the Markov process induced by our random walk on this set. So namely, we take that one, we take its image by the generators, and we take the image by the generators, etc., and we consider almost of them with respect to the convolution measure, to the measure given by the random walk. And so I will just say, in general, what is the behavior of that. So just don't forget for a minute that we are in an open set where the bifurcation current vanishes. So here, for instance, we are in the region of U of bifurcation. And here, we are in the region of stability, let's say. So what is a heuristic? So I am really sorry for my drawings, it's really bad. But so what is a heuristic? If you take a generic random, so you start with a horizontal graph, and then you take a generic random sequence on your group, and you look at the image. This is going to be something which here is going to behave well, and here is going to oscillate a lot, and this is going to be something like this. Okay, and here one can prove that the area. So I will state something which is true for any open set. You take an open set, and you look at time n at the average array of the graphs that you see above that set. This grows linearly with n. It is equivalent to n times the measure of the bifurcation current if we are in, let's say, dimension 1. So it is linear if the bifurcation does not vanish, but if it vanishes on the open set, it's sublinear. Why? Because we look at the average. So let's call that graph A. No, sorry. We call that graph Rn G at. So we take the average volume of so let me write for you the formula, and we will see that this has to do with the bifurcation current. It's quite easy, in fact. So what is this average volume? You take the integral, so on the set of passes, so on G to the n, okay? You make an average on all the words of length n, and here I will write what is the volumes of 1. It is the integral on U of ddc of log of the norm of A of Rn of G applied to a point Z0. So the point Z0 is a point here on the sphere. So we have this. And here, what you see is that this quantity is the pullback of the Fubini study form. So here, in fact, we have to take, so this is true to the power. So we have to take the power P of that form. And this is true because that 1-1 form is the pullback of the Fubini study form on the Riemann sphere by the map which assigns to a representation A the point A of Rng of Z0. And so you see that this quantity converges, this quantity has a heuristic of n times the Lyapunov exponent of A. So when you divide by n and you take the ddc, you see the bifurcation which appears, and this says exactly that the average volume of that of these graphs grows linearly if the bifurcation current has mass on U, and grows sublinearly if the bifurcation current vanishes. And so we now come back to our situation where exactly the bifurcation current vanishes on U. Okay? So we know that, in fact, the average volume of these graphs is a sublinear, but in fact, by using exponential convergence of the convolution operators on each of these P1s, I really don't go into these details, we can indeed prove that the average volumes of these graphs is bounded. And then we can, by some argumentations, extract from a majority of them some subgraphs which converges in the sense of Bishop, using Bishop's theorem. If we know that some complex manifolds have bounded array, some sequence of complex manifolds have bounded array, we can extract some subsequence. And 1 minute, I tell you the argument for the second step. there is, in fact, it is a direct consequence of the double ergodicity theorem of Kajmanovic. Which says that I will state this theorem for a random walk which is symmetric, because it's easier. If you have a symmetric random walk, you look at the action of the group G by diagonal action on the product of two copies of the Poisson boundary. So, and there is this measure class, which is a product of the stationary measures. This action is ergodic. This is a statement of Kajmanovic. Now, how do you conclude? It is a nice argument. It's really easy, nice argument. Look at the function defined on G times G. I call it intersection, which to a couple of elements of G. So sorry. So it is a map defined, sorry, not on G, of course, but on the Poisson boundary. And in fact, I'm sorry, in fact, in E times E. But E is a subset of full measure in the Poisson boundary. So we are going to associate to that a number, which is just the intersection number of the graphs of theta corresponding to G1 and the graph theta corresponding to G2. And of course, this function, so in fact you take two elements here and you associate the number of intersection points. It is invariant by the diagonal action of G. So it is constant almost everywhere. And in fact, you can take the intersection in any compact set. So to any compact set, you have an integer. This is, and this defines for you a measure with integer values. So the only possibility is like this, is that in fact this measure is the sum of Dirac masses, and it says you that the graphs don't intersect apart from a finite number of points. So apart from that finite number of points, you have a holomorphic motion, and then we are close to the result. So that's the argument, which is correct. Okay. Thank you.
More questions or comments?
I think that with the exception of the last result, there is a very big intersection between what you said and what Christian said. Because in your case, you were putting this probability measure, this product probability measure on the words. And what he would, so if you consider a suspension of a Schottky group over the sphere minus a finite number of points. So you take the sphere minus a finite number of points. That's a free fundamental group. Then you suspend, as he explained, that representation. And so he obtains in the same manner as you do with these AIs.
Sure, it's the same thing, exactly.
He obtains this foliation in the Riccati equation, and then his sigma plus was exactly this map you were
exactly.
So in that sense, that's the same. Now, the one thing which is different is that here you were considering the product probability on the generators. You took one up to AGA, one inverse up to AGA inverse. You put 1 over 2n to each one, and you took the product.
Yes.
Here, the probability space is given by the geodesic flow on the sphere minus this finite number of points. There's even a moduli. If you move the points on the sphere on which, so here this diagram that you drew, And in some sense, then, that's why I was bothering you.
I understand.
I'm sorry for bothering you. If there was a geometric meaning for your Poisson boundary, in his case, the Poisson boundary is the circle at infinity of the disk.
Right.
And then you can see many of the things. I mean, that part of the talks where, I mean, you could make an immediate translation from one to the other, but you're speaking about different probability spaces, no?
Right, but what you say, in fact, so you can, so I have no time, but you can translate all what is done here with discrete random walks into a word of continuous word using Brownian motion, or which is quite close geodesic flow. And if you do that, I mean, there are applications. I mean, it's nice what you obtain, but I have no time to.
No, but there has to be a difference, because in this case, this depends on the conformal structure of the points on the sphere that you remove to take the representation. Here,
right.
You fix the representation. In the other case, you can move the geometric position of the points of the base.
Yes.
So you're considering different. So in some sense, your result does not translate. So let's say you cannot obtain as a corollary of what you explained now in the set work of Christian's saying, because the probability space is different. Here you do not depend on a conformal structure of a complement of a finite number of points, which were your generators.
Yes, but you know,
it
okay.
depends on this. So and then also, as he mentioned, instead of proving this Ibarge and this other person you mentioned,
Fürstenberg?
Yeah, Fürstenberg, right? So we had to reprove this theorem, but not for this dynamics, but for hyperbolic dynamics.
I see. But you know, Fürstenberg here has invented a really nice thing, which is you take the Brownian motion, which is almost the same as the geodesic flow, and he constructed a discretization measure, I mean a discrete process on the fundamental group, which encodes the Brownian motion. So in fact, you can translate like this results that you obtain from discrete random walks into results that you obtain from geodesic. Yes, of course, it will depend on the conformal structure, this discretization process. So, but I mean, this is not, I mean, it's not completely evident to make the connection, but. No. Fürstenberg proved that in the beginning of the 70s to prove that a lattice in a higher rank group is not free. And he exactly did that. He constructed the discretization of the Brownian motion to get a boundary map and to begin this kind of Margulis things to